so here's a brief recap of what we've been doing in the last class. Okay, so like I pointed out, if you want to get good codes with d greater than or equal to 5, okay, you need to go beyond needs fields beyond binary. Okay, so that is the first observation. And I just told you and you believed me, right? So I didn't really prove it or anything. I just said it's not very easy to design for d greater than or equal to 5, and finite fields of size larger than 2 give you a very nice solution. Okay, so that was the motivation. So we wanted to see if there are fields which are finite and then they are larger than 2. First of all, why are we interested in fields? Because we want to design linear codes, which means we want to talk about linear combinations, row space, column space and all that. So naturally we have a field, I mean we want to look at a vector space and a vector subspace, so we need a field, and that field has to be finite. Why should it be finite? Only then you can represent it with bits, right? Otherwise if it's infinite like real numbers and all that, then when you can't represent it with bits very easily. Okay, so finite fields make a lot of sense from that point of view. Okay, so the only finite field that we saw so far is Fp. Okay, what is this Fp? It contains the set 0, 1, 2 so on till p minus 1, and addition and multiplication are integer addition and multiplication modulo p. Okay. So I can give you some simple examples for how this works, but I am assuming you are reasonably familiar with what I mean by modulo p. Okay, so when I do modulo p, I am going to divide by p and take the remainder. Okay, so I multiply two things. If it goes outside of the set, what will I do? Divide by p and take the remainder. I will come back to the set. Okay, so that's how we do the field operations, and it's easy to show. What are the things that are easy to show? For addition, properties are easy to show, right? So you can show inverse and identity identity etc. All these properties can be shown quite easily. Okay, for the multiplication, inverse is a little bit tricky. Okay, and I had an argument towards the end of last class. Basic idea is, if you take any a which is between 1 and p minus 1, okay, and then you look at the set a times 1, a times 2 so on till a times p minus 1, okay, there are no repetitions. Okay, so basically this set has no repetitions. Okay, this modulo p, of course. Okay, remember it's all modulo p. Okay, I am using the same dot, has no repetitions. Okay, all of them are non-zero, they lie between 1 and p minus 1, and there are no repetitions, which means clearly there exists I such that a dot I equals 1. Okay, so that was my quick argument for saying why this has to work. Okay, why cannot there be repetitions? Okay, so for instance, if ai equals aj mod p, yeah, so then you get some factor. Okay, so either you get, this will imply p divides a into I minus j. Okay, and that cannot happen, I mean, so did I get that right? Yeah, so something like that. Okay, so I know it's a quick and dirty argument, but I guess this is not correct. So if this were to happen, see, remember both I minus j and a are less than p. Okay, and the product has to be 0 modulo p, which means the only way it can happen if p is p factors. Okay, since p does not factor, this cannot happen. Okay, so this will imply p factors. Okay, so let me just simply write it that way. Okay, so this implies, okay, p can be factored. You have to look at the cases very carefully and make this argument rigorous, but like I said, in our study of finite fields, we won't see too many proofs that we rigorously write down. I will quickly give you an idea of why it works, and there are several books which you can look up which will do a good job of writing down the proof precisely. Okay, so this is the way it works. Okay, so FP becomes a field. Okay, so you can see a few examples if you like of this. I do not think I did any example in the previous class, but you can see a few examples. For instance, F3 contains 3 elements 0, 1 and 2, and if you want to show how the addition operation works, you can make an interesting looking table, put 0, 1, 2 here, 0, 1, 2 here, then show how the addition operation works. Okay, so remember it is modulo 2. Okay, so this is how the addition operation would work. Then if you want to show how the dot operation would work, once again you have to do 0, 1, 2, 0, 1, 2. So anything multiplied by 0 will give you 0. You can show that in any field that is true. Okay, if you have the additive identity, you multiply any non-zero number with the additive identity, you will get 0. Okay, so these things can be proved using the axioms. I guess it is reasonably clear why you are calling it 0, right? You are calling it 0 because when you multiply, everything becomes 0. Okay, so this is 1, this is 2, this is 2, and this is 1. Okay, so all the properties that we were talking about works out. Okay, so this is how the addition operation looks. Okay, you can write down similar fields, similar tables for the other fields if you like. Okay, F5, F7 will just look a little bit more complicated. Okay, this is the easiest one. I was able to do that. Okay, so the other example that we saw was of course F2, which was 0, 1. Okay, all right. So when you initially see these fields, okay, there is some kind of an inclusion. I was saying you have to think about one field containing another field. Okay, so it is very tempting to say F2 is contained in F3. Okay, so as sets it is true, but in actual nature it is not true. Okay, so why is it not true? See, the one in F2 is very different from the one in F3. Okay, so I want you to think about that for a while, and then I will tell you why that is true. Okay, so you cannot think of F2 as being a subset of F3. Okay, so this is a wrong notion. Okay, the set 0, 1, of course you can imagine the integer set subset 0, 1 definitely is contained in the integer subset 0, 1, 2. As long as you are thinking of integer addition, all that is fine. But when I say F2, I am assuming addition modulo 2. When I say F3, I am assuming addition modulo 3. So the operations are different, and that makes the elements also different. Okay, for instance, in F2, what would happen to 1 plus 1? You would get 0. In F3, 1 plus 1 is 2. Okay, so clearly the 1 has a very starkly different behavior. Okay, 1 plus 1 becomes the additive identity in F2. 1 plus 1 clearly is not the additive identity in F3. Okay, 1 plus 1 would be what? The additive identity. Okay, so you should not think as inclusion. Think of this as inclusion. Okay, so in the other fields that you might be familiar with, we always write Q is contained in R, right? Is this okay? Yeah, this is okay. The rational numbers are contained in real, and the operations are all similar. Okay, when the rational numbers act exactly as they are supposed to, even within the real numbers. You can also say the other inclusion. Okay, you can also include the complexes, and that would also be a valid field kind of inclusion because the operations are respected. Okay, so this inclusion is dangerous. Okay, so it's a wrong notion to have, and you should know the difference. Okay, all right. So that's FP. Okay, it turns out there are also other finite fields. FP is not the only finite field. You can have Fp power m. Okay, for any m, you can have Fp power m. Okay, so we will see the construction soon enough in this lecture, but before that, we need this idea of polynomials with coefficients from some field. Okay, so I did introduce it in the last class, but I want to go through it once again. We will denote by fx polynomials of this kind, right? a0 plus a1x plus a2x square plus so on till an x power n. Okay, what are all these ai's? Ai's belong to f, which is of course a field. Okay. So, this is the set of polynomials in the field f. Okay. So, once you have, for instance, a of x and b of x in the field, you can do several operations with them. Okay. The first operation, which is the easiest, is of course addition. Okay. You can do this. This also belongs to fx, and I am assuming you know how to do addition. Okay. So, you look at the like powers and simply add the coefficients, but here the addition should be in the field. Okay. So, do not simply say modulo p, because it should be the addition operation in the field. Okay. It could be some other operation, I do not know. Right now it is modulo p, in most cases it will be modulo some prime number, but in general in an abstract way you have to think of it as the addition operation defined in the field. Okay. And you can also do multiplication, a of x times b of x. Okay. This is also something which belongs to the set of polynomials with coefficients from f, right, and I am assuming you know how to do the multiplication. Okay. So, it is you have to multiply term by term, it is very easy to define, it is the same multiplication you have done for polynomials all along, but once again what will change? The coefficients you have to multiply using the multiplication in the field f, and then when you add, you should also add using the multiplication in the field f. Okay. So, various things can change drastically in this multiplication. Okay. I will give you a simple example. Okay. Suppose I look at x plus 1 as belonging to f2x. Okay. What is x plus 1 multiplied by x plus 1? Okay. And try that, and if I think of x plus 1 as belonging to, let us say, f3x, what is x plus 1 times x plus 1? Okay. So, let us do a slightly different multiplication, I am sorry, let us do x minus 1 times x minus 1. Okay. So, sorry for this, just a bit of a difference, just to make it a little bit more interesting. Okay. What is x plus 1 times x plus 1? Okay, it is simply x squared plus 1. Okay. So, if you think of x minus 1 belonging to this, and the third example is if x plus 1 belongs to f3x, then what is x plus 1 into x plus 1? You get x squared minus x plus 1. You can write it like that. Can I write it like this? Okay, x squared plus 2x plus 1, but what is 2 in f3? It is minus 1. So, I can also write it as minus x. Okay. So, these are all just simple ways of writing it, just to make the answer look nicer. Okay. What about x minus 1 times x minus 1? X squared plus x plus 1. Okay. I wanted the answer to look nice and in a nice form. So, you see how multiplication changes character when you think of the coefficients as coming from different fields. Okay. So, it is a little bit strange. Okay. Then the third operation, which is also very crucial, is division with remainder. Okay. Arbitrary divisions are not possible in fx. Okay. You can't define a division which will divide any b of x by a of x and then give you some other element in fx itself. Okay. It will only be rational. Okay. So, we will not worry about that. We will only be worried about division with remainder in fx. What is division with remainder? You can divide b of x by, a of x implies you do that long division. Okay. When you do that long division, you will get two other polynomials, q of x, a of x plus r of x. Q of x is called the quotient, r of x is called the remainder. What is the property? Important property, degree of r of x is between 0 and it is less than degree of a of x. Okay. So, these are the various things about polynomials that you should be comfortable with. Okay. The next notion, I think I wrote about that notion also, but let me remind you once again, is about roots or zeros. Okay. When do you say x naught in f is a root of a of x belonging to f x? if a of x naught is equal to 0, right. So, you plug in x naught instead of x, evaluate that whole thing. Why can I evaluate it? I can evaluate it. This evaluation is meaningful because x naught belongs to f, okay, and the coefficients of Ax also belong to f. So, every multiplication is well defined and it can be done in the field f. Okay. So, for instance, if a of x belongs to f2 of x, there is no meaning in putting x naught from f3, okay, because there is no compatibility, there is no multiplication defined between those kind of elements. Okay. So, you have to restrict yourself to suitable fields, that is important. Okay. So, this is 0. Okay. Is there a question?
Yesterday we said that if you want to look for the roots, then you can go for near fields as well.
Yeah, but it should be a proper containment. Okay, okay, the question was, what about the statement that if you have a equation with coefficients from rational field, then you can plug in a real number for the x, right? You can do that, but then the rationals are contained properly in the reals. Okay, the operations are meaningful. Okay, but f2 is not properly contained in f3, right? So, the operation is different. I just showed you the example. Okay, so, 1 is very different in f2 than f3. So, you can't do such strange things. Even though I motivated them as integers, suddenly when you think of 1 in f2, it is not an integer anymore. It becomes some other entity. Okay, so you have to notice those differences. It's a bit abstract. It's important to know the difference. Okay, we use the same notation for multiple things. That is the problem. Okay, all right. So, this is equivalent to something else. This implies x minus x naught divides a of x. Okay. So, what do I mean by x minus x naught dividing a of x? If you do the long division of a of x with x minus x naught, your remainder will be 0. Okay. So, this is true in any field and the proof is very easy. How will you prove it? Let me see. How are you going to prove it? Okay. Yeah. So, basically what you have to do is, suppose a of x naught is 0. Okay. One way is very easy to prove. If x minus x naught divides a of x, then what happens? How do you prove this way? If a of x is q of x times x minus x naught. Okay, so you put a of x naught, this term is going to go to 0 and 0 multiplied by anything in any field is 0. Okay, I did not rigorously prove these things, but these are true. Okay, so believe me. So you have to prove it, you can prove it. So this will show clearly a of x naught is 0. The other way around, how do you show that? The way to do it is, you have to take a of x and divide by x minus x naught. Okay, what will be the degree of the remainder? It has to be degree 0, right? So it will be a constant. Okay, right, because it has to be strictly less than the degree of what you are dividing by, and that will be a constant. Okay, so what are you getting? A of x equals q of x times x minus x naught plus some constant. Okay, so let us say r naught. Now what do I know about a of x naught? It is going to go to 0. So clearly r naught has to be 0. Okay, so this implies a of x naught equal to r naught equal to 0, and you get this x minus x naught dividing a of x. Okay, so these are just, I mean, I am sure you knew this in your gut, but if you have to prove it, you have to write it down, right? The careful proof has to be done, and the division algorithm is the one that gives you the proof. Okay, so this is the reality. Okay, so this is quite important. Yes.
Is it guaranteed to have a root?
No, not really. Okay, so I said if x naught is a root, then this is true. I never said every a of x has a root in f. That is definitely not true. Okay. All right. So that's the next definition. He asked me the questions. I'm going to go to the next definition. Okay, a of x in fx is said to be irreducible over f. Okay, is said to be. This is the definition. Irreducible over f if what? If there is no root for a of x in f. Okay. Then you say it is an irreducible polynomial. Okay. So that is the example. Okay. Yes.
That are irreducible over f, when you multiply them, that will still not have
Okay, so I know this is a slightly bad definition. So let me change this definition. Okay, so if there is no, see this is not wrong. This is not an if and only if. You know, if there is no root, yes, it's irreducible. There's no problem. That's why I said it's a bad definition. But if it is irreducible, it doesn't mean that there is no root. That's not the only condition. You can also have multiple. If it doesn't factor, it's not reducible. Okay, so this is true, right? Is it true or not? Okay, actually, so let's rephrase this. This is a very bad definition. So let me not change this. Okay. Okay, so let me change this. I'm sorry for that. Let me take it back and let me write the careful definition first. Okay, so it's irreducible over f if it cannot be factored. Okay, so I have to say something about it. So let me say that. Okay, so let's do this. Okay, irreducible over f if okay, let me just say f x cannot be factored. Okay, factored into a of x equals, let us say some, I do not know, f of x into g of x, okay, where, thanks for pointing that out, so both these guys belong to f x and degree of both of them is greater than 0. Okay, so you need that. You cannot have a constant. Okay, so you can always take out constants, that is not a problem, but you should not be able to take out a factor. Okay, so you are right. So that is true. So one needs to be careful over an arbitrary field. Okay, it cannot be factored only if this is true. Okay, so it's a vague definition, but usually the way you check it for at least smaller degrees is to see first if it has a root. Okay, and then you have to do some additional checks. It's not as easy as I said, so you have to do this very carefully. Okay, so it seems like a complicated way to write it down. So let's see some examples, and then some examples it will be very clear. Okay. So why are we worried about irreducible polynomials? Okay, so if you notice, if you look at fp, how did we get fp? We had prime numbers, right? So what's the property of prime numbers? They cannot be factored. Because they cannot be factored, we got fp roughly, right? So that is the reason why we got fp. If you go back and see the proof, the main proof is with multiplicative inverse, and that came because p cannot be factored. Okay, so it turns out when you work with irreducible polynomials, you can similarly define fp power m. Okay, so we will use irreducible polynomials to define fp power m, and these are polynomials that cannot be factored. Okay, so let's look at examples, and the simplest examples are degree 2 examples and over f2. Okay, so we'll mostly look at f2 of x only, and we'll look at some degree 2 examples. Okay, so I'll look at f2 of x, and let's say if I say degree equal to 1. Okay, so if I say polynomials of degree 1, first of all degree 0 doesn't make much sense. Okay, so let's not worry about it. Degree 1 with coefficients from f2x, then the form is what? a0 plus a1x, a1 is 1 and then a0 is 0 or 1. Okay, so you basically have just how many polynomials? You have 2 polynomials of degree 1 in f2x. What are the 2 polynomials? X and 1 plus x, and both of them are irreducible, right? Can't reduce x and 1 plus x. Okay, hopefully it's clear. I think that's okay. Okay, and then if you say degree 2, what happens? Okay, you have 4 different polynomials of degree 2. Okay, what are the 4 different polynomials? X squared plus 1, x squared plus x, and x squared plus x plus 1. Okay, so there are 4 different polynomials, and it turns out 3 of them are reducible and 1 of them is not reducible. Okay. So, for degree 2 the checks are easy. Okay. So, if at all a degree 2 polynomial can be factored into 2 polynomials of degree at least 1, the only way it can happen is 2 degree 1 polynomials. Okay. So, you can easily plug in roots and check. Okay. So, all you have to do is put in x equal to 0 and x equal to 1 and see if you get a 0. If for both cases you do not get a 0, then clearly it will be irreducible. Okay. So, this is one of those cases where it is very easy. Okay. Also the factoring is also easy, it is not too difficult in this case. Okay. So, it turns out this guy is irreducible. Okay. Or everything else is reducible. You can also find the factors very easily, but also another check is to see if there are roots. Okay. So, x equals 0 is a root here, x equals 1 is a root here, and then x equals 0 and 1 are roots here. Okay. So, that is something that you can do. So, if you say degree equals 3, okay, there are 8 different degree 3 polynomials, right, and you can keep on writing them, but it turns out polynomial x cube plus x plus 1 and x cube plus x squared plus 1 are the 2 that are irreducible. Okay. Everything else I am quite sure reducible. Okay. You can check that out. There are some simple conditions. For instance, 1 has to definitely occur in a irreducible polynomial, otherwise x can be definitely factored. Okay. So, there are some rules, and for binary there has to be only an odd number of terms. Okay. And in fact, for degree 3 also you can simply put in x equals 0 and x equals 1. Why is that? Can have only 2, I mean if it factors into 2 factors, one of them should have degree 1, right? Both cannot have degree greater than 1. Okay. So, definitely there will be one root. Okay. Remember my previous equivalence, root is the same as a degree 1 factor. So, if you have a root, then there is a degree 1 factor, if there is a degree 1 factor there is a root, and that adds up being the same. Okay. So, these are irreducible polynomials. Okay. So, what's a little bit non-trivial, but it can be proved with some effort, but not very easy, is for an arbitrary degree, if I say degree equals m, there exists. Okay. So, what is this crazy symbol that I drew? Let me say there exists irreducible polynomials. Okay. So, for every m there exists at least one, for instance, in fact in even the number you can exactly count. Okay. There exist irreducible polynomials for every m. Okay. So, that is a good thing to know. Okay. Just like we know there are prime numbers, there are infinitely many of them. For every degree m there are irreducible polynomials. Okay. So, that is the first non-trivial result. We may not really prove this in class, but it is true.
So, this is for any field?
Yeah, it is actually for any field, but I have written it down for F2. Okay. So, this is true for any FPX. Okay. So, there are algorithms to find these irreducible polynomials. You can look it up in computation software like MATLAB, for instance. There are methods to find it. Okay, MATLAB may not have it, but Mathematica or something will definitely have lists of all irreducible polynomials for any FP. You can go look it up. Okay. So, these are irreducible polynomials. So, from now on I will assume that I can always find an irreducible polynomial of degree m in FPX. Okay. So, let us just see a few more interesting points here. If I move to F3x, okay, degree 1 is a boring case, we will not see it. Let us go to degree 2. Okay. How many polynomials are there for degree 2 in F3x?
18.
Okay, 18 different polynomials. 18 different polynomials, because see it has to be a0 plus a1x plus a2x square. This cannot be 0. Okay, so there are two possibilities here, times 3 here, times 3 here. So, that will give you 18 different possibilities. Okay. So, you can go through this, there are several irreducible, but for instance this polynomial, okay, 1 plus x square is reducible. Okay. So, it is not irreducible. Okay. It is easy to see, one of the roots is what, x equals 1, you put x equals 1, it is a root. In fact, this is, we saw just before, this is the same as it's a, I think 1 x minus 1, no, sorry, I am always thinking in the binary field, so keep writing the same. So, x minus 1 squared is 1 plus x squared, did not we see this? Yeah, we saw the multiplication just now. So, it is clearly reducible. So, this is another indication that F2 and F3 is not a proper containment. Okay. So, it is something else, so strange things can happen. When you think of the 1 in F2, it is very different from the 1 in F3, okay. One needs to be careful about that. Okay, alright. So, now we are ready to see the construction of Fp power m. Will it surprise you or not? Okay, no. Okay. So, I mean I will just give you the construction and show that it is a field, that is okay. Later on maybe we will see some properties. Okay. So, this is the construction of f p power m. It is also denoted, like I said, GF p power m, a Galois field after a famous French mathematician Galois. Okay. What is the construction? It goes like this. It is basically a set of all polynomials of degree m minus 1 or lesser. Okay. So, I am not saying these things are non-zero, ai belongs to Fp. Okay. So, this is the set, alright. What does the set contain? I have not defined addition and multiplication, that is the crucial part of definition of a field. Let us just look at the field once again and the set first and then make sure we are comfortable with that. What does the set contain? It contains polynomials with coefficients from Fp, okay, of degree less than or equal to m minus 1. Okay. How many such polynomials will I have? Okay. Each coefficient can take one of p possible values. So, clearly p to the power m. Okay. So, Fp power m is okay, not made a mistake there. Okay. So, it is Fp power m. So, the crucial part is addition and multiplication. Okay. So, addition will be what? Just regular addition, okay, addition in fx. Okay. So, there is no problem there. So, you see all the properties are satisfied, right, closure is satisfied. You add any two polynomials of degree less than or equal to m minus 1, you will definitely get a polynomial of degree less than or equal to m minus 1. Okay. There is the 0 polynomial which acts as the 0, and every element also has an inverse. You simply do minus of that, you get the inverse, and it is also in the same field, there is no problem. Okay. For multiplication, you will need an irreducible polynomial. Okay. Okay. So, multiplication is polynomial multiplication, it is basically multiplication in Fpx modulo some pi of x, where this pi of x is a, I should say what pi of x is. So, you should have a pi of x which is a degree m irreducible polynomial. In Fpx. Okay, so, this is crucial, just like we had p before, you need a pi x which is an irreducible degree m polynomial. Is that okay? All right. Yeah, there can be many, yes, but it turns out you have only one field. So, those are surprising results, we will come to that later. Okay. So, you pick any one degree m irreducible polynomial in Fpx and use that to define your multiplication. So, how will I multiply now? If I have two elements from fp power m, I will first multiply like they are polynomials in fpx. So, I will get maximum degree what? It can go up to 2m minus 2, okay. So, it can go up to that, okay. And then what will I do? I will divide that, I will do a long division of that with pi x and take the remainder, okay. Now, what will be the remainder? Degree less than or equal to m minus 1, because pi of x has degree m, okay. So, that is the idea in saying multiplication in fpx modulo pi of x, okay. So, clearly closure is obvious, there is no problem, only non-trivial thing is inverse, okay, and the inverse, the same proof like I did before will go through, there is no problem, okay. You can go back and check that proof. You take any one polynomial in this, multiply by all the other polynomials, okay, you will see that there are no repetitions. If there are any repetitions, then your pi of x would not have been reducible, okay. So, from there you claim that there will be one polynomial which will multiply and give me 1, that is it, okay. There is no problem, okay.
So sir, but how do we know that irrespective of whatever phi I choose, I should be getting the same?
No, I haven't come to anything about it. This is just for, as far as the definition is concerned, it is a field, right. So, that is all I am claiming right now. Okay. All right. So, let us see some examples, see a couple of examples, then we will. Is it okay? This is the definition. I am not going to show that this is a field, okay. So, please write it down if you like. I have given you the motivation for where the proof comes from, but these are the operations, okay. So, for instance, if you have to write a C program to implement the field, this is what you really need to know, okay. It is very easy to write. In fact, you can very easily write a C program which will implement a FP, okay. FP is very easy, okay, right, and then FPX is also very easy, okay. You do the multiplication and then you do the long division, you have FPX also done. FP power m is simply FPX. Once you have the addition and multiplication with remainder, or multiplication and division with remainder, you are done, okay. You can do a very simple computer implementation, okay. So, kind of that is the focus of this course, at least whatever you see here, you should be able to write a program to implement it, okay. Whether you do it or not, that is my goal at least, okay. So, that is the focus with which I am teaching. If you want to know the theory behind it, you have to read some textbooks and get comfortable with it, okay. You are free to ask me some questions, I answer to the best of my ability, but there are books which have all this written down very clearly, okay. So, let us see some examples before I tell you some more interesting things about these fields, okay. So, few examples, okay. What about F4? Okay, without knowing anything about anything else, you can write down easily the elements of F4, right. It is very easy. What are the elements of F4? Yeah. What are the elements of F4 again? Go back and look at it. See, p power m, 4 is what? 2 squared, right. So, p is 2 and m is 2, okay. So, that is the first step, okay. So, I have recognized p is 2 and m is 2, and F4x contains what? Polynomials of degree less than or equal to m minus 1 with coefficients from F2x. So, this contains polynomials of degree less than or equal to m minus 1, and what is m minus 1? 1 with coefficients from F2x, F2, sorry. So, this is just a small set, okay. How many do you have? You have 4 different elements clearly, and what are them? 0, 1, x, 1 plus x, okay. So, those are the 4 elements in this, okay, and you can make an addition table. Addition is very trivial, okay, you know how to add, okay. So, you just add any 2, you will get something else which is in this list only, okay. Slightly non-trivial addition is x plus x. What will be x plus x? 0, right. So, in fact, the moment you have p equals 2, irrespective of what m is, you add 2 elements, what will you get? You repeatedly add the same element, what will you get? You will always get 0, okay. Any a plus a in f2 power m will be 0, okay, because you have 2 times that, and 2 is 0, that is 0, finished, okay. So, that is the idea. So that is addition. Addition is trivial, so we will just leave it alone. Okay, it is easy to see what the addition is. You can make a table if you like. Okay, like I did before for F3, I made a table, so you can do that if you like. So you can do a table. It's very easy to do the table. So let's make the table. We will do that. Okay, 0 1 xn 1 plus x, 0 1 xn 1 plus x. You can go ahead and fill out this table. It's not very hard. Okay, so that's the table you get.
So, sir, F4 doesn't exist, but F4 of x exists.
No, I'm sorry, I'm not writing F4 of x. No, this is F4. I'm sorry. Thanks for pointing that out. That's not F4 of x. That is definitely F4. Okay, I hope I didn't write F4 of x there. It's Fp power m. Sorry, F4 of x is also exists, but that's not this. Okay, that is different. Okay, so this is F4. I'm sorry for that mistake. Thanks for pointing it out. Okay, is that clear?
We say F4 means the elements are not from 0 to 3, but they are 0, 1 and x and 1.
Yes, definitely. So for instance, the question is F2 is 0 1, F3 is 0 1 2. Shouldn't F4 be 0 1 2 3? Okay, that's not correct. Okay, that's not correct. That's not defined. That will not be a field. Why will that not be a field? Yeah, for instance, 2 does not have an inverse in that. If you do mod 4. Okay, so the question was, is this a field? 0 1 2 3 addition and multiplication mod 4. Okay, it's not a field. Okay, so this guy is not a field. Okay, the reason is 2 does not have a multiplicative inverse. Nothing that you multiply by 2 will give you 1. Yes or no? Yes. Okay, so that is the problem. This F4 and this guy is called usually Z4. Okay, that's the notation for this. Z4. It turns out it's a ring, but it's not a field. Okay, so it doesn't have inverse. Okay, so that's the problem. Okay, so that's addition. Addition is quite simple, and Z4 and F4 are totally different. Okay, they are not at all the same. Okay, remember that. Okay, 3 plus 3, for instance, 0, not 0 in Z4. Okay, 1 plus x plus 1 plus x is 0. Okay, so you don't think of that as. So they are very different type of things. Don't even, there's no easy relationship between them. Okay, there are complicated relationships and many papers have been written on it, but easy relationships don't exist. Okay. Okay, so let's say we are now interested in multiplication. Okay, what do you need for multiplication? You need an irreducible polynomial of degree m, which is in this case 2. Okay, so you might want to pick any one, but you can't pick any one. There's only one irreducible polynomial of degree 2 in F2, right, and that is x squared plus x plus 1. Okay, so with this you can try and make a table for multiplication. Okay, but you don't have to do long division and all that. Okay, so I will teach you a easy little shortcut. Okay, so it's very easy, not very hard. Okay, remember when you do modulo pi of x, you are thinking of pi of x as equal to 0. Okay, when you do modulo something, it's roughly the same as thinking pi of x is the same as 0. Okay, so what should you think of x squared plus x plus 1? It is equal to 0. Okay, so if x squared plus x plus 1 is 0, what is x squared? Minus x minus 1, but it's the same as x plus 1. Okay, so x square equals x plus 1. Okay, so that is the magic mantra to use. Okay, once you use that, your multiplication will be very, very trivial. Okay, when I do modulo, when I multiply two polynomials modulo pi of x, all I am using is this additional rule that x square equals x plus 1. Okay, so once you use that, you can easily make a multiplication table. Okay, so mod p of x or mod pi of x is equivalent to having the condition x square equals x plus 1. So once you do that, the multiplication becomes very easy to write down. See how I got that? I did it in my head, but if you write it down, you will see that's what the answer will be. All right, everybody is happy? Okay, so next example, we are going to see F8, okay, and here I am going to make a switch in the notation, okay, and that makes everything more complicated. Suddenly you will see everything will be much more complicated. What is the switch in the notation? Instead of x I am going to use alpha, okay. So from Latin letters, the moment you go to Greek letters, suddenly everything will become much more complicated, okay. So it is very common to write finite fields with alpha instead of x, okay. So x sounds like a variable you might want to use, right. Eventually I want to write f4x also. I want to think of polynomials with coefficients from f4. If f4 also has x, then the notation becomes really nasty, okay. So that is the real reason why they do it, but suddenly because of alpha everybody thinks you have a much more difficult problem than what you had before, okay. It's the same thing as before, but I am going to shift it to alpha, okay. So what is f8? You have 8 different elements, okay. Each of them are polynomials in alpha of degree what? Less than or equal to 2 and coefficients from f2, 0 or 1. You can write it down, it is not very hard, 0, 1. Is that okay? Okay. So this is F8. Okay, I am not going to labor with the table for addition. I think addition is okay. We are also not going to labor with the table for multiplication, but we will do some multiplications by hand, okay, just to check how things are working, okay. So for doing multiplication, I need to define a pi of alpha which is of degree 3, okay. So I told you there are 2 different choices that you can make for pi of alpha for degree 3, okay. So we will pick alpha power 3 plus alpha plus 1, okay. You can also pick the other one, and like I commented briefly, you do not really get a new field, okay. Those things we will not prove, but it's any one is good enough, and we will pick the nicer looking one. I think alpha plus 3 plus alpha plus 1 is nicer. Do you agree or not? No? Okay, so pi of alpha is this, okay. Okay, so you can do any multiplication, but what is the rule that you will keep in mind when you do multiplication? Basically alpha power 3 is alpha plus 1, okay. So that's the only rule you have to remember, okay. But remember, in the multiplications you might also get alpha power 4. So then what will you do for alpha power 4? So it is basically alpha times alpha power 3, and alpha power 3 you know is alpha plus 1. So basically alpha power 4 is the same as alpha square plus alpha, okay. So if you use these 2 rules, any multiplication becomes very trivial. So you just write down these 2 rules, always remember them, and any multiplication you do, whenever you get alpha power 3, replace it by alpha plus 1, whenever you get alpha power 4, you replace it by alpha square plus alpha, that is it, you get your answer, okay. So that is how you operate in F8, okay. So in reality it is a much simpler field than the real field, okay. So if you learn about the real field and all its complexity, you will really get scared, okay. It is a scary field, okay. Somehow we are more comfortable with the real field than this abstract field, okay. It after all has just 8 elements. What can really go wrong with 8 elements, right? Absolutely nothing. Real numbers between 0 and 1 has how many elements? Uncountably infinite number of elements, okay. So it is just much more scary than this, but somehow people get more scared of this silly field than the real field, okay. In fact the name real is the most unreal of all, okay. It should not have been called real. I do not know why they call it real, okay. If you read the actual definition of the real field, you will agree with me, okay. So it is not real at all, it exists in somebody's imagination, okay. So I want you to do a certain specific type of multiplication, okay. So it is interesting, and you will see a nice little pattern emerge about these fields, which is also universally true, which once again we will not prove, but we will accept as fact, okay. So the multiplication I want you to do in F8 is the following. I want you to find, okay, you have 0, you have 1, you have alpha, you have alpha square in the field, and then I have alpha power 3 being equal to 1 plus alpha, then I have alpha power 4 which is alpha square plus alpha. What I want you to fill out is alpha power 5, alpha power 6, alpha power 7. Okay, we will stop there. Okay, did everybody converge on the answer? So alpha power 5 is what? Okay, so it's basically alpha power 3 plus alpha square, and then alpha power 3 you have to replace by alpha plus 1. So essentially you will get alpha squared plus alpha plus 1, and then alpha power 6 you have to multiply alpha power 5 by alpha, so you would get alpha squared plus 1. Okay. In fact, there is a curious way to go from here to here directly. How will you do that? Yeah, so basically square it. 1 plus alpha squared is simply 1 plus alpha squared, the 2 goes to 0. Okay, then alpha power 7 is what? Is alpha? Alpha? No, it's 1. It's 1 again. Okay, then what will happen to alpha power 8? Alpha. Okay, after that it will repeat, the same thing will repeat again and again. Okay. So what we have seen is alpha power 7 equals 1 in F8. Okay. All right. That is the first thing that is obvious from this table, from this calculation. There is another slightly more subtle thing. If you look really carefully, you will notice what I am saying. What is that other subtle thing? What is? Yeah, all the elements of F8 are simply being generated as powers of this 1 alpha. Okay. So that is the other subtle thing here. So I wrote previously F8 as this. How did I write F8? Okay. See, I wrote F8 as this guy, right? Okay. I wrote F8 as, okay, I wrote F8 as this, no? Okay. So anyway, the cutting and pasting is not really working out quite well because the size I am not able to adjust, but anyway, so let me write it again. I wrote F8 as 0 1 alpha 1 plus alpha, alpha squared plus 1, alpha squared plus alpha, alpha squared plus alpha plus 1. Okay, and then I wrote down the rules. Alpha power 3 equals, the rule alpha plus 3 equals 1 plus alpha. Okay, I was able to figure out the field based on that. It turns out the same F8 is the exact same as 0 1 alpha, alpha squared, alpha power 3, alpha power 4, alpha power 5, alpha power 6, and then I have to remember 2 rules now. Alpha power 3 is 1 plus alpha, and then alpha power 7 is 1. Okay. So what is so nice about having 2 different ways of writing F8? Okay. If you have to do addition and multiplication by hand, in the first notation, in the top notation, this, okay, in the top notation, okay, in this notation, what is easy, which operation is easy and which operation is difficult? Okay, if you want to do by hand, addition is very easy, but multiplication is little bit more difficult, right? It is not difficult really, but it is little bit more difficult. You have to do a long division, do some rules and remember something. In this notation, what is very easy? Multiplication is very trivial, okay, but then what is difficult? Addition is not very obvious. Alpha power 5 plus alpha power 4, you have to work a lot to get the answer if you do not want to use the other notation. In fact, you will end up going to the other notation, okay, to do the addition. Okay. So when you implement finite fields, this table is very critical. How do you go from what is known as the polynomial notation to what is known as the power notation, okay. For F8 at least we have seen, but we wonder if this is true for any Fp power m. It turns out it is true, okay. Turns out there is one element of Fp power m which will generate all the elements as consecutive powers, okay. So all those things are true, we will see them later, okay. So right now just want you to look at these two things and convince yourself that multiplication is easy in one notation while addition is easy in the other notation, okay. So that is F8. Okay, so an exercise for you is to try the same thing for F16, okay. So F16 you pick pi of alpha to be alpha power 4 plus alpha plus 1, okay. So this is irreducible, okay. To check that you need to do a lot of work, okay. What is the work you have to do to check that this is irreducible?
Check.
Take all 2 degree
Yeah.
irreducible polynomial.
Yeah, so you have to do that. So you have to take first of all linear factors, right. So alpha equal to 0 is not a root, alpha equal to 1 is not a root, so there are no linear factors, okay. And then you have to look for factors of degree 2, it is possible that it is a factor of degree 2, okay. And you will see there will be no factor of degree 2, okay. For instance, alpha square plus alpha plus 1 will not divide this, okay. So then you can be sure, yeah, that is the only thing you have to check, it will not work, okay. So once you check that you are done, okay. If it does not divide that, this will be irreducible, okay. There are other reducible polynomials, in fact there are 3 irreducible polynomials of degree 4, okay. The other one is basically the mirror image of this. What is the mirror image of this? Alpha power 4 plus alpha power 3 plus 1, okay. And then the other polynomial that is irreducible is alpha power 4 plus alpha power 3 plus alpha squared plus alpha plus 1, okay. All these guys are also irreducible, you can take any one and try, but you will get a surprising answer for this one. So don't try this too early, okay. Try just this alpha power 4 plus alpha plus 1, okay. This will work, okay. Try this and try making this equivalence, 2 different notation. It is a good exercise, okay. The first time you do it you may not believe me, you should not believe me, you should try it. It is not any element, okay. So let me come back to that, I am going to come back to that, okay. So this alpha is a little bit special, that is why you got this equivalence, okay. If you take any other element, all its powers will not generate all the, even in FP it is not true, okay. So let us see a few more computations just to get your feet wet with this, okay. So in F8 let us try something which is interesting. What will happen if I try something okay. F8 is a little bit weird because all elements will be good, okay. So let's go to some other field, okay. So we will take okay, let us see another example which is slightly more intriguing. We will try what can we try? What is the next thing you can try? Tell me something. F9, okay. So that seems like the next simplest thing you can try, okay. So let us try F9. F9 okay, let us try F9, okay. So F9 is going to be 9 elements, okay. So 0, 1, 2 and then alpha, 2 alpha, what else, alpha plus 1, alpha plus 2, two alpha plus 1, 2 alpha plus 2. Did I get all 9? Okay, so remember 9 is 3 power 2, so I have to look for all polynomials with coefficients from F3 of degree less than or equal to 1, okay. So all linear polynomials, okay. So addition I will skip, okay. So addition, you know how it is going to work, it is a little bit non-trivial, okay. So when compared to F2, okay, so F8 or F4, addition is a little bit non-trivial. Okay. So, for instance, alpha plus alpha is what? 2 alpha, it does not go to 0, okay. That is what I mean when I say it is a little bit non-trivial. Okay. So if you add 3 times, what will happen? It will go to 0. Any element added 3 times will go off to 0, but just 2 times will not go to 0. But beyond that, there is nothing much to say about addition. Okay. So, hopefully addition is clear to you. For multiplication, you need irreducible polynomials of degree what? 2 with coefficients from f3. Okay. So, it turns out one choice which is a weird choice is alpha squared plus 1. Okay. Is it okay? So, it is irreducible in f3. Okay. In f2 it is clearly not irreducible, right, but in f3 it is irreducible, you can check that. So, if you put in 0 you get 1, you put in 1 you get 2, if you put in 2 you get 2. So, it is irreducible in f3. Okay. So, if you now go ahead and do the multiplication, you will get a proper field, you know, I mean you do multiplication modulo alpha square plus 1, the only thing you should remember is what? Basically alpha square is 2. Okay. So, you remember alpha square is 2, you can do the multiplication. Okay. It will be consistent, you can find, you can fool around with it and try to find various things. Okay. Let us try something just for fun. What is the inverse of alpha? What is the multiplicative inverse of alpha? Okay, additive inverse is very easy. Additive inverse is what? Minus alpha or 2 alpha. What about the multiplicative inverse? Try that, it is a bit of, I mean I do not want you to intelligently get to the answer, but at least try a few things till you get to the answer. Okay, 2 alpha, is that right? Okay. What about the multiplicative inverse of alpha plus 1? Okay, you can't find that very easily, right? So, what else can we find very easily? Okay, so let us just stop here. Okay, it's okay. Multiplicative inverse is a little bit boring, so you can leave it like here, leave it right here. Okay, so the other thing we tried before was to look at powers of alpha. So look at what happens when you do powers of alpha. It's a little bit, yeah. So look at what's happening. So you get alpha, then what is alpha squared? It's equal to 2. And then what is alpha power 3? 2 alpha. What is alpha power 4? 1. That's it. You don't get all the F9 elements. Okay, so that's dangerous. Okay, so maybe something is wrong with the statement I made, but you should try alpha plus 1. Okay, so I think alpha plus 1 will work here. If you take alpha plus 1 and try all its powers, okay, it's a little bit boring to try that. Okay, so you try all these powers, I believe you will get okay. So 0, 1, okay, I believe this is the same as F9. A nice way to check that is to see if alpha plus 1 power 4 is 2. Okay, so that's a nice way to check that. Is this true? Is this true? You can check this. If this is true, then this will also be true. Okay. So can someone check this? Alpha plus 1 power 4, is that equal to 2? Is that true? It's true. Okay, so this will mean that alpha plus 1 power 8 is what? See, remember 2 is minus 1, don't really get confused by 2. Okay, so 2 is minus 1 in this. So alpha plus 1 power 4 is minus 1, that implies alpha plus 1 power 8 is 1. Okay, all right. So this is the rule. Is it okay? Did anyone else also check this? This works out? Okay. So this is correct. Okay. Okay, looks like there's lots of discussion going on. Everybody happy? Happy? No? Okay, let's try this. What is alpha plus 1 power 3? This is the easiest computation. Okay, it is 2 alpha plus 1. How did I get that? This is the same as alpha power 3 plus 1, 1 power 3. Why is that true? Remember your binomial formula, right? What are the other terms? They will have 3 choose 1, 3 choose 2. Okay, all those things will be multiples of 3. Okay, and they'll all go to 0. Okay, and 3 is my magic element in F9, right? 3 makes everything go away. Okay, so power of Trinity, as they say. So just it makes everything go away in this. Okay, so alpha power 3 we just now wrote down as 2 alpha, so it's 2 alpha plus 1. It's very easy. If you want to do alpha plus 1 power 4, you have to do that, and you'll see it's 2, which is minus 1, and this is 2. Okay, so even for F9, when I pick alpha square plus 1 as my pi of alpha, I am not getting alpha to be my magic element which creates all the elements as powers, but alpha plus 1 is a magic element, and that's good enough. If I have a table going from the notation on the top to this notation, I can do both addition and multiplication easily. Okay, so it can happen. Okay, so as it turns out, instead of alpha squared plus 1, if you pick, okay, if you pick pi of alpha to be alpha squared plus alpha plus 2, for instance, okay, is this a valid irreducible polynomial? It is a valid irreducible polynomial, there is no problem there. So if you were to pick pi of alpha to be alpha squared plus alpha plus 2, it will turn out, what will happen? Okay, alpha itself will end up generating the entire F9. Okay, alpha F9 will be equal to 0 1 alpha alpha squared, so on till alpha power 7. Alpha power 8 will be 1, and alpha square will be 2 alpha plus 1. Yeah. So I'll write down the general fact soon enough, but these are things to keep in mind. Okay. Okay. So what we have shown by example now, we have proven by example, we have not really proved it, but what we have proved by example is fields of the form fp power m seem to have two different ways of representation. One is the simple polynomial representation over fp, which is very useful for addition. The other is this power representation, what's called a power representation. There seems to be one element which is able to generate all the elements by its powers. Okay, and this statement is in general true for any fp power m. Okay, so what you have to do for that is you have to pick your pi of alpha smartly. Okay, and that choice is what is called as a primitive polynomial. Okay, so what is a primitive polynomial? Okay, an irreducible polynomial say pi of x of degree m is said to be primitive if the smallest n for which pi of x divides x to the power n minus 1 is n equals, okay, so I should say where this p of x comes from, say f p x is n equals p to the power m minus 1. seems like a crazy definition. It is a bit of a crazy definition if you see it without all the motivation that needs to come from other areas. We will just take it as a definition, and you can go back to our examples with F9. Okay, this pi of alpha squared plus 1 will divide, for what n will it divide? X power n alpha power n minus 1. Use one of your formulas. Okay, a squared minus b squared is a minus b into a plus b. You use one of that, you will see for n equals 4 that will divide. Okay, and 3 square is 9, and you want the smallest for it will divide will be 8. Okay, so for 4 itself it divides. Okay, so that pi of alpha did not qualify as primitive. On the other hand, this pi of alpha square plus alpha plus 2 will be primitive. Okay, so that is the example. Alpha square plus 1 is not primitive. Okay, of course in F3 alpha. Okay. So this example is for F3 alpha. Okay, don't spend too much time digesting this definition. Okay, it's not too crucial. What is very crucial is, if you pick pi of alpha as a primitive polynomial, first of all there exists a primitive polynomial for every p and every m. Okay, that is the first point. Okay, what are the 2 points that are important to remember? There exists a primitive pi of alpha for all Pm. Okay, so there is a primitive polynomial. Not only is it irreducible, it is also primitive. There exists a primitive polynomial. These also can be looked up in Mathematica, etc. Yes.
Will that be like unique, or can
There can be many primitive also. Okay, so there exists at least one primitive pi of alpha for all Pm. Okay, and then the next thing that is true is, if pi of alpha primitive is used to construct FPM, then FPM will be A0 plus A1 alpha plus so on till AM minus 1 alpha power m minus 1 AI belonging to FP. Okay, and it will also be equal to the set 0 1 alpha square so on till alpha power p to the power of m minus 2. Okay, alpha power p to the power m minus 1 will be equal to 1, pi of alpha will be equal to 0. Okay. 0 1 till oh no. So okay, so some of these powers will be equal to 2. I mean, for instance, there will be some I such that alpha power I is equal to 2 if p is greater than 2, for instance. If p is, for instance, 7, there will be some I for which alpha power I equals 2, and there will be another j for which alpha power j is 3, etc. These are the elements. All the elements are generated by this. Okay, so this is true for, I have written it for p power m. This is also true for Fp. Okay, so we never really saw Fp. For even for Fp, this is true. Okay, this does not really apply in this. No, I mean, yeah, of course it applies, but you have to think of Fp as being generated with a degree polynomial degree 1, which is always primitive, and then you can write it down. Okay, so for even for Fp, this is true. Okay, so there is always a primitive element. It's a little bit difficult to find. Okay, there are all kinds of results about primitive elements. Okay, so I'll stop here, digest this, pick up from here in the next week.